degree. What you see? Completely different phase behavior. What do you see? You see there is a monoclinic zirconia that is predominant now, 63% versus here 0%. What does it mean? Just take the powder and press it to a pellet. The tetragonal phase is full, 100% monoclinic is zero. Don't make it a pellet, don't give it a shape. Okay, just calcine the powder at the same sintering temperature. What you get? You get full monoclinic. You get 63% monoclinic. Okay, so what does it mean? It means that when you shape the system, the total strain, we are aware of these Williamson Hall effects and all these equations and Shearer and all these, where we used to calculate the lattice size, lattice strain, and all these. Through this work, we showed that total strain in a shaped body include a new term, and that is, we have talked about doping strain. We have talked about, this is Shearer, right? This is due to the size. Okay, this is due to lattice strain. So you can talk about even Williamson Hall, and then you have thermal strain. We are talking now in terms of a shape strain for the first time. We showed that if when you have these shape it in a constraint, there is a shape strain, and that can mitigate a phase transformation, that can control a phase transformation. When that can control a phase transformation, you do not see any unwanted phase happening over there. How did we do? This is just this year we have published with one of my PhD students, Lakshman. Show. So this is what we published this year on on this theory. So this time what we're doing the same method. We're doing the same method, and what we did is magnesia, yttria, gadolinium, and calcia, all 4 mole percent. We made the powders. What we saw that in magnesia case there is a mixture of tetragonal and monoclinic phase. In gadolinium yttria, it is fully tetragonal. In calcia case, there is some amounts of monoclinic phase coming up. Okay, monoclinic phase here. Otherwise, tetragonal. Then what we did, we sintered it. This is sintered tablets. In the sintered tablet, what we saw that there is yttria and gadolinium same as their powders. That means now this is no more, the grain size has increased, of course, because you have shaped and you have heat treated 1250 degree, but they retain the tetragonal phase. In the case of magnesia, what we saw that no, it is fully, it is still predominant. There is tetragonality is there, but monoclinicity is also there. In calcia, you see that there is predominantly, not predominant, fully tetragonal. Okay, fine. Then you see the same, just calcine at 1250. This is sintered at 1250. It's calcined at 1250. When you calcine at 1250, you see the biggest change. The Mg remains similar. Y remains yttria, Y2O3 remains same. Gadolinia remains the same. Big change is in calcia. In calcia, what you see that there is full of monoclinic phase appearing, and here there was nothing. So why calcia came out as such a successful story? The reason is here. So we analyzed the ratio of grain sizes from the sintered ceramic to the 600 degree calcined powder. Okay, and what we found? Well, we found that from magnesia to calcia, actually this ratio is decreasing. In other words, calcia as a dopant from magnesia has the highest control in restricting the size of the sintered grains in the tablets. And when you control the size, when you control this size in the sintered body, what you can do, you can now improve the tetragonality. Magnesium has lowest control. That's why magnesium has lowest amount of the tetragonal phase developed. And this, once you have more control on this, when this size you can control its minimum, you can have maximum amount of tetragonality. So this is the blue one, is the ratio of tetragonal phase from the ceramic to the 600 degree C calcined powder. So you can see then now this is increased. And how calcia is capable of doing this? Because we found out and we have shown that calcia has highest control in grain boundary mobility of the zirconia grains. That's how you control the zirconia grains in here using calcia. When you can do that, then you have this success. So we understood that all our processes, out of that calcia became stabilized, and calcia got stabilized because of this method. So then this 4% or 3%. Now, if you see the calcia doped zirconia ceramics, previously people were doing it 8% and 16%. We just doing it 3 or 4%. So less than half or 1/4 of their amount we are using, and we are making this tetragonal phase stabilize. Tetragonal phase, as I said, important for dental applications, mechanical properties, thermal barrier coating, and many others. We are using this tetragonal phase stabilization using calcia dope zirconia 3 to 4%. We took this work forward, and then we are showing here with 3%. So anyone, you can choose 3 or 4% of calcium stabilized zirconia. Here also you can say that we make the ceramic that is phase pure tetragonal, and we can see that there is Raman, there is no tetragonal, no monoclinic phase appearing. And now this is the beauty. We have in Syria dope zirconia, we showed that there is a grain size control of 170 degree. Here we show the grain size control of 170 nanometers. Here it is less than 100 nanometers. 90 nanometers, if you can control, it is below 100 nanometers. It is only 90 nanometers in the sintered grain size, even after a heat treatment of 1210 degrees C. That is the beauty of the process. When you can control these grain size and control them below 100 nanometers, then what happens? You can actually take the advantage. This is what Garby has said in his predominant pioneering work in 1965, that size controlling the phase stabilization in zirconia. We can see the tetragonal phase is now stable. Okay, mechanical properties we tried, we studied, and we saw the first thing first is the fracture toughness. The fracture toughness we measured with microindentation. We found this 5.6 MPa root meter, and that is very much the 3CATZP, we are calling it 3 calcia doped zirconia ceramic, and that is very much similar, if not better, with the previous reports. The reports are listed in here for the last 40 years. What we are comparing it with? Always 3Y. That means Y2O3, yttria stabilized zirconia, 3% yttria stabilized zirconia. This is a popular grade now existing in the market. Existing in the market, this is a popular grade. This is the so-called best grade, yttria stabilized zirconia 3%, and we are comparing all our results with the best, with the popular one in the market. Okay, so we say that 3CATZP and 3YTZP, our mechanical property in terms of fracture toughness data, are very similar. Okay, then these are the two tests we did, one very relevant for the biomedical, the dental ceramic applications. What is that? They call it as a low temperature degradation test. So they do it at either high pressure, high temperature, low temperature, or ambient pressure for high hours. Here we did the boiling water, 84 hours, 3.5 days. You have to put the one sintered target completely immersed in zirconia, in boiling water, and then run a slow scan and see if after that you don't do any grinding polishing, just soak it with a tissue paper, run the XRD immediately. Do you see, even at slow scan like this, scanning at 2 seconds per step involving a step size of 0.02, do you see any monoclinic phase? No, we don't. We don't. Another, we did experiments of more than 4 days, just low temperature degradation, heat treatment. This zirconia ceramic is known for such that if you do low temperature less than 250 degree, but for long hours, 100 hours, we did for 4 days, more than 4 days. If you continuously put that, do you see the monoclinic phase appearing there? We don't see. So this is the robustness of our sintered ceramic target. Why our result is important? The reason is here. You see this test people have done, right? LTD, low temperature degradation in the hydrothermal conditions. For all 3%, 3 mole percent ETS stabilized zirconia, and you can see the amount of monoclinic phase that they have got from 4% to even 50%. How much do we have got? Zero. We have got zero. And again, I will refer to, I believe the beauty is here. When you control the grain size below 100, none of them are controlling the grain size below 100 nanometer. When you control the size, you can achieve a lot of properties, which is phase shift tetragonal here. Size is controlling the phase transformation. Okay. Then, in terms of other properties, how do our system, that is CAO stabilized zirconia, compares with the popular grade that is made in the world today, that is ETS stabilized zirconia, and what is there. So here is our work. What you can notice from there, our hardness data is comparable. Our toughness data with 3 mole percent CATZP is again comparable. Our grain size is lower, but what most important industrially is we are achieving a similar density like the 3Y TZP system, but at 250 to 300 degrees below, 250 to 300 degrees below than the traditional sinter. So there is a remarkable savings of the heat economy, and that is where the strength of our result is. When you compare with the very few works people have done, with only one we could find, that is true on 2018 on calcium doped stabilized zirconia, where you can see that the 3 mole percent here, and they have done with even with double 4 and 6 mole percent here, but even then they could not find fully tetragonal phase like ours. Our hardness is also much better than theirs, and grain size, I think this is a connection with low temperature sintering compared to any other. So we got the similar density, but our grain size is much lower compared to them. Why this work? Why this work is at all important? Well, before I say that, just this is, we are also working with this 10% for the cubic phase stabilized. Till now, whatever we have got a mixture. We have got a mixture of cubic and tetragonal phase, and we are still working. These are very initial results. These are very introductory results, so I will not talk about more. But one thing I can say, even with 10% CO stabilized zirconia, we see there is no monoclinic phase even with slow scan XRD. There's no monoclinic, it would appear here. There's nothing. Even with Raman, we don't see there's a much of monoclinic here. Why this result is important, whatever we have been doing and whatever I show it here. See, first thing first is the yttrium. So when you have yttria, that is yttrium, yttria stabilized zirconia, uh, that is 28th most abundant metal on Earth's crust. Okay. Calcium is the 5th in the same category. So when you replace yttrium or yttria with calcia, there's a remarkable saving on the economy and of course availability. Now let me expand this issue of availability on and economy. In terms of availability, all the yttria, that is the rare earth, whole of world buys yttria. Who makes this? Tosho, a Japanese company, has monopoly on this. But rare earth, who is the rare earth supplier? China. Because world's 90%, close to 90% rare earth reservoirs are with China. So when we have to buy the yttria stabilized zirconia, we have to import this. And importing this from China, from Japan. Or there is a company in Germany, Sulzer Metco. They also make this. But again, the source being yttrium or yttria, that makes it that expensive. Well, how expensive it is. Let me give you an example. 1 kg of 3% yttrium stabilized zirconia cost you in today's term around 70,000. Okay. And 1 kilo of calcium stabilized, 3% calcium stabilized zirconia, based on our precursor rating, if you do, will cost you maximum up to 1,500 to 2,000. So 70,000 versus 2,000. What you would choose? Well, of course, depends on what properties do you get. And this is the thing that has made many industries interested in our work. Our prime minister today, these days, constantly on the days of COVID, have been talking about Atmanirbhar India. If we can make this in bigger scale, we don't have to rely to China or Japan for importing this material, the doped zirconia. We can make it because calcium is everywhere. India is one of the richest source of calcite. India is poor when it comes to the rare earth doping. So we can get this from our own land by our own process. Second, the calcium is also integral part of our bone. So when you dope calcium, we take antacids. Antacids have calcium oxide. We all know all these. In other words, when you dope calcium in zirconia, that is supposed to be more biocompatible, isn't it? Compared to a rare earth element like yttria, right? Third is our process, that is ensuring 250 to 350 degrees of heat economy. Now take it to the industry and ask them what this 350 degrees of heat economy means to them. Crores of money. Okay, and that too ensuring a full densification at low grain size below 100 nanometers. And even if you take today the Yttria from Tosho or Sulzan Metco at 3-4% mole doping, you see a phase mixture of monoclinic plus tetragonal. If you take our powder at 3-4%, it is phase pure tetragonal. Exactly what you need for all the properties involving mechanical applications. Finally, our tributes to the great starting from Garbi, who is no more. He died in 1980 in the 90s, but he was the first to pave, inspire us through his work in 1965. We have just taken. Then there's Ivy Chen in UPenn, who talked about the role of different dopants and their phase stabilization in zirconia. In 90s, he has done predominant work. There are few works who got published in Science as well. And of course, Professor Alexandra Navrotsky, she's no more now in Davis, she's now in Arizona, who there are plenty of reports in Science by her where she has talked about size dependent phase transformation in ceramic materials in oxides. What we have done, we have combined all of these three, and we have found our own process in that way. So I would end this presentation with our tributes, sincere tributes to all three of them. And just what we were saying, that our work has make interested an industry on ant ceramics. So IIT Patna, for the first time, we have made a patent, we have done this technology transfer from IIT Patna to ant ceramics. We've shown interest uh, on making these powders to a large scale in multi-kilo, in tons and stuff. So we have to transfer the technology successfully, and now we are working together to how to make this technology more successful and coming to the market. Carol Zircolite, there's a company in Gujarat, and Dent Lab, there's a company Indore, and there's other companies in Bombay. So I'm in touch with some of those companies. Carol Zircolite particularly has shown great interest in our composition, which they want to make teeth, uh, the dental zirconia applications. They actually manufacture this, make these teeth. They want to make teeth with our composition, and start utilizing their with a variety of other tests to see the viability if it can be directly come to the market. Because if it can be, then one teeth of zirconia would not cost 10,000 anymore. Okay, so the 10,000 rupees for one teeth of zirconia predominantly because of its choice of precursor. When you minus the yttria, when you take the yttria out and stabilize it with something else with similar properties, then you don't want. And of course zirconia is the best. Why it is the best? There are plenty of reports that why zirconia teeth is the best. I'm not going to that direction, but if you can stabilize that, you don't have to rely or pay 10,000 for a zirconia crown, uh, a particular zirconia teeth. So this is, in a nutshell, this is our research theme. So we work on the process structure correlations and structural analysis on high temperature materials, where we study mostly the process and the structure, how process, alters the structures, and fascinating mechanisms involving the synthetic processes, be it burst nucleation. Today I have shown some faceted nanostructures we have got without surfactants, uh, some different non-classical arrangement of nanocrystals, thermal analysis, phase analysis, defect studies, sintering, and textured studies. Today I've showed mostly on the burst nucleation aspect. And these are the property that we do mostly at proof states, the catalytic, photocatalytic, conductivity, electrical, and some mechanical properties. Materials that we have talked about, we have been working in zirconia-based systems with varieties of doping. I've showed some of them. In Syria, it is another material that we have been working very closely for last 6-7 years, and also some works on copper oxide. This is our work on Syria zirconia system that got selected first, DST Young Scientist Project, and in the compendium book published by the DST Secretary, Professor Ashutosh Sharma at Kanpur. Um, Professor, it was 53 projects nationwide was selected based on their performance of the project, and our project nationwide was one of them in the category of engineering sciences. And these are with this, I acknowledge my group members, my institution, that is IIT Patna, my department, for giving me wholehearted support, funding, and whenever any other resource is needed. Also, I would like to thank my group members, all my PhD students. So initial works, they started with Kundan, who is now in South Korea doing his postdoc, and the present works that I showed today, the process devised by Aditya, and then Lakshman is also working. So these two students are working on the zirconia project. My collaborators around India, in IIT Kharagpur, BRC Mumbai, and Bardhaman, and IIT Bhubaneswar, and also University of Warsaw in Poland. With this, I thank you for your attention.
Uh, Thank you very much, sir. Can you hear me?
Yeah. Thank you.
Yeah, so thank you for very much, sir, for your wonderful talk. So we have a 5 minutes for discussion and questions. So the students are requested, please ask the question if you have any. A student, please.
Good morning,
Yeah.
sir. Uh, yeah, yeah, sir. My question is that first you have congratulate to you for your DSC recognition,
Thank you.
sir. Actually, when you dope calcium with zirconia rather than a
Mhm.
resistance matter, means incidentally you can select, or you select that on the any properties belonging to calcium.
Okay, good question. Good question. If you see the progression of our work, if you see the way I presented, so Aditya, my student, was first was trying on. He started with Syria zirconia, as I showed at 10,000 rupees. 20% Syria doped zirconia. In the 20% Syria doped zirconia, he chosen, why he chose? He chose because that in dental ceramics, people, there are many companies which prefer to make Syria doped zirconia because they want to try. Syria has been shown to be more biocompatible. So he was initially said that, okay, sir, I want to try my recipe with Syria doped zirconia. I said, fine. When it worked, I immediately asked him that you please try this in calcia and magnesia. Why did I say that? Because I say that if you can make this property, or if you can show the same thing with magnesia and calcia, then it will be a wonderful thing because of two reasons which I said. Calcia and magnesia, they are most, calcium and magnesium, they are most abundant compared to cerium and yttrium because both are rare earth. Okay, so immediate first choice is the availability, and you don't have to rely on China or any foreign country for the resource. India, when it comes to rare earth doping, India has it poor in resource. That's the same reason why we started Kundan started with zinc. Other than the photo functional properties, we have a rich source of zinc, India. But rare earth source and rare earth things, resources, it is world's resource, 90% is with China. Okay, so why to make these things doped and take the resource from a foreign country? So I said immediately, I said that, okay, you have to make, we have to now make this with calcium and magnesia. Why? Because they're so cheap. And number two, as I said, calcium and magnesium, you are taking daily base antacid based on these two, Ca2 plus, Mg2 plus. That means it is going inside your body. It is going inside your body, and there is no harmful interactions. Also, calcium is a ingredient in your bone. So that means if I dope things with calcia, then they are supposed to be more biocompatible. So there was not random choice, but you can see that our funda, the way that we tried, wanted to, failed with magnesia, but it clicked with calcia. Why it clicked with calcia? That also we studied, and that also we reported. And the fact that we have worked with on calcia was such a low doping and making equivalent properties, that is where the cost comes down. And I would finish your comment or question with a note that in India, the whole world sees in India that, okay, India is all about economic research. So whatever we do, India will do reverse engineering, and India will find out, okay, I have done it with 1 crore rupee, India can do it in 1000 rupee. Here we are showing, no, we are doing the research with economy, yes, but without compromising the property. And that is the whole factor which made the industries interested. See, in 8 years time in IIT Patna, we have been working on many such systems. None of them has interested the industry like this particular composition. Okay, that's why, be it
Okay.
the zirconia manufacturers, be it the industry with dental ceramic manufacturers, they all got interested. That's all. Thank you.
Yeah. So any other question?
Yeah, again, sir, I am Ashwani Kanbor.
Yeah.
Sir, actually, my question is regarding my doubt of I want to do PhD. Then how can select my MTech project to change into
Yeah.
PhD? That will benefit
Yeah.
for me.
Yeah.
And for
Yeah.
that, just I am asked the previous one question. That's why that I am little bit confused to select the material to work on project.
Okay. Well, for that, I can only say
Thank
that
you.
I'm not aware of your
Yeah.
topic. I'm not aware of your topic once. So then you must be working with respect to under some supervision, the topic, and
Okay.
based
Yeah.
on the recent current literature, and your supervisor and the teachers around, they can help you better because I don't know much
Yeah.
about your topic,
Yeah.
so that I
Yeah.
can comment on it.
Please.
Sorry
Yeah.
about that.
We are running short of time. So question from others, if you have quickly, one more question we will take, one or two question, couple of question. No? Okay, since we have no more question, so before concluding the talk, we have to give the vote of thanks. So this is the formalities we have to do. So first of all, thank you very much to Dr. Anirban Chaudhary for giving the time in a very short notice. We are really thank you, sir. We don't have a word to say about this. And please convey my thanks to Dr. Manoranjan sir. He actually
Yeah,
gave the reference to about you. So please, so actually this talk was organized as a part of as we are celebrating 11th foundation day of our university. So this talk was as a academic activity we have to organize. So this is as a part of activity. So on behalf of the Aryabhatta Knowledge University, I really thanks to you. And thanks to first of all our honorable Vice Chancellor for his wholehearted support, and officers and all our student. I hope they all will be benefited, and and yours the yours objective for Atmanirbhar Bharat. Really, it is very generous and great contribution you are delivering for making our India to success as a Atmanirbhar Bharat and technology transfers for improving our health, basically dental dental's problems. We were very least bother about dentals our dental care. So since you enlighten how we can improve the coating of the tooth, so this is really wonderful work. And sir, you also shown the how we can improve that technology for your others doped zirconia doped materials, and how we can make revolutionize using the nanotechnology and and material and with material science. So really it is really your talk was very helpful to us. And uh, in last but not least, I thankful to all of our teams and our all our dear students who have participated and joined. And I hope in future we will organize this many more talks related to our nanoscience topic and others and related to material science. And I'll hope and I please accept, sir, our one more invitation so to visit our department. So then we
yeah,
will have a lot of opportunity to discuss what we are doing, so we can move ahead. So once again, I thank you very much, sir, and I thank you to all. Thank you very much.
thank you, Dr.
Yeah,
Ravi, and
yeah, yeah.
also I thanked Dr. Manoranjan Kar sir also, and I told him that he called me also on the same day you sent me the email. He called me, so I said
Yeah.
okay. Yeah, of course I was not that prepared because I have never given this talk. So I thought that okay, if I have to give talk and you have put in nanotechnology and not nanoscience, so I said okay, technology this has a relevance that has a nano also. So for the first
Yes,
time, I'm
yeah.
giving this. I've never given this talk. Okay, I was just
Good.
working. I've never given this talk. So I just took this challenge and said, okay,
Okay.
we'll do that. And also, yeah, because okay, for last 1 year, I'm doing all these. I also, as a part of invited member, I teach this. NITTTR at Chandigarh, where I'm teaching the faculties from private colleges and all. So
Yes.
I used to, when I go into this Google profile or all something, I used to see, 200 plus, 300 plus members and stuff. But here, so I always prefer a kind of a full house. But here, maybe it's a short notice or something, not many people. So I always see that I want to I want to reach many people through this work,
Yeah,
and
yeah.
I want the more students to be there and stuff. So
Yes, sir.
whenever
Yeah,
I get a chance, definitely I would love to do in person,
yeah,
and I want to communicate and want to see, because here I can't see people's reaction. I can't see
yeah.
you know
Yes, sir. Yeah, yeah.
their
Yes, sir. Yes, yes,
that
sir. Yeah,
so those
yeah.
things I'm
So,
doing, but
yeah,
what to do. But definitely,
yeah.
definitely in future, once these
Yes,
COVID restrictions are a little bit
yes.
normalized, and again
Yeah,
the
yeah,
cases are increasing,
yeah.
so we just have to be cautious and all. So I also thank you. I also thank you very much for this opportunity to share our work. Okay,
Thank
thank
you
you
very
very
much,
much.
sir. Shall we close the
Thank
session?
you.
Okay. Thank you
Sure,
to all.
sure. Thank you.
Yeah.
Thank you. Thank you.